Okay. Hello, dear Meatbags. Now is our final lecture on hyperbolic geometry and its applications. And today we are going to talk about some advanced computational techniques in this geometry. Also about how hyperbolic neural networks were constructed, at least for now. But this very side topic from our main talk. Mostly we will talk about some mathematics. Okay. So we last time we talked about some applications, and actually personally, for me, this course is already useful since I have taken several ideas from applications for my research. From applications lecture, I mean. Okay. So let's see what we did. Actually, since we are all coming, let's have a look on the exercise that I gave you, that I failed to do on the third lecture. So it was here. So this was about metric tensor, how to do what? Where is it actually? Yeah, compute metric for hyperboloid at point given by this. So actually I will continue working with metric tensor today. So let's do this first, and next we will continue with what I'm going to do later. So okay, let me switch the screen. Okay, so previous time I made a mistake. So, and for now, let me improve in your eyes. So this is an exercise, and and we had something like, yeah, here. So exercise is about to translate a metric, and so the mapping, actually I forgot where was this picture. Not quite sure for now. Okay, sorry. Let me copy it directly from Google. Yeah, here it is. So okay, let's compute the metric transition for this between these two modules. So, yeah. So, what are the modules here? So, this is a hyperboloid of given by equation as sorry, not this equation. However, okay. Oi. Yeah. Yeah, like this. Okay. So, and this is plane given by x0 equals 1. This is a point minus 1, 0, 0, 0. And this is a central projection from this point of hyperboloid onto this point. Oi, x0 equals 0, sorry. Okay. So what we did here? So here is point x0, etc., xn, and here we have a point 0, y1, etc., yn. Okay. First of all, how to compute with differential tensors? Actually, we can differentiate our equation and this gives us differentiation of constants which equals 0, and this equals to minus 2x0 dx0 plus 2x1 dx1 plus 2xn dxn. So we have a relation between dxi's. And here we have such a metric this on this model. So like this. So we should write it as ds square equals to 4 times dy squared sum over I divided by 1 minus sum over I yi squared, and this all squared. Yeah, here is the metric. So actually first let us compute this translation function, what it is. So how to compute y's from x's. Okay, so actually I made a mistake last time. So this vector here equals to x0 plus 1, x1, etc., xn. Right? Is everything visible? Tell me. So not everything is visible. Okay. So this is something like this, and we have a proportional vector collinear with it, so it is like 1 and y1, etc., yn, and so they are proportional. which means that this is вот так. Окей. 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 Оно подключится вообще как само Paint? То есть оно в Paint подключится или как? Я не понимаю. Да. Просто будет экран. Ну тогда у меня не будет вот этой картинки. Откуда она у меня будет?
Ну, как мышка. Посвети, просто он симулирует нажатие в нужную точку экрана.
Ну хорошо, давайте. Sorry about this delay. Окей. Окей. Правда, мне нужно будет сменять цвета. Ну ладно.
Нажатие мышки.
Я понимаю. Вот. Окей, sorry. So we have this vector as okay. Actually, can't use your hellish hardware. Sorry. So those vectors are proportional to each other, and this means that we have something like k equals to x0 plus 1. Мой почерк вообще не лучше, честно говоря, чем то, что я делаю. Okay, so we have like yi equals to xi over x0 plus 1, which means that what? So let's compute dyi. This is sort of differentiation over any argument which y could be function of. So this is like derivative for this function, and this equals to dxi over x0 plus 1 minus x0 sorry again xi dx0 divided by x0 plus 1 squared, right? So and actually we have equation like this, so let's remember it. I mean this initial equation, and yeah, so sum of dyi squared equals to sum over I of dxi. Let's divide it already by x0 plus 1 squared, xi minus xi dx0, x0 plus 1 squared. Okay, so now this equals to sum of dxi squared divided by x0 plus 1 squared, which with minus, probably first of all sum of xi squared x0 squared divided by x0 plus 1 horsepower, and minus 2 sum over, well, here is sum over I, sum over I, sum over I, dxi, dxi, dx0 divided by x0 plus 1 cubed. Yeah. And actually, we already had an equation that 2x1 dx1 plus etc. plus 2xn dxn equals to 2x0 dx0. So, and this is what we actually see like here actually. So you see probably this expression here, and this all equals to sum of dxi squared over x0 plus 1 squared plus sum over I. So actually, yes. So here sum over I for I not equals to 0. I forgot to mention it, but probably you understand. So here we have actually sum over xi squared. This we also know actually. Sum of, from here we see that sum of xi squared equals to x0 square minus 1. Yeah. So let's use it. So actually we see some of so this is like x0 squared minus 1 dx0 squared over x0 plus 1 fourth power and minus this expression 2x0 dx0 squared divided by x0 plus 1 cubed. I hope that something will okay. I actually hold. Yeah. Actually, also we have something like this. So dx0 equals to sum over I xy divided by x0 multiplied by dxi. This is from here. So actually we might square it like this. So and this will okay. Boy, this won't give us anything. So now I'm confused. Again, I made a mistake probably. No. So this was what we did. Wait. This is cubed. This was cubed here. Okay. So something will. Yeah. So something will subtract. So we have something like this. And here we have something like x0 minus 1 divided by x0 plus 1 cubed dx0 squared minus 2 x0 dx0 squared over x0 plus 1 cubed. And now something is subtracted. So we again have something like this. And now what? So this equals to minus what? Minus dx0 squared divided by x0 plus 1 squared. Okay. Seemingly always correct, but I thought that the metric will be different actually. No. Yes, actually we didn't divide, or actually now we just computed this thing. So everything is not lost for now, since we have to multiply by 4 and divide by this denominator. So our metric is something like 4 times of this expression divided by 1, divided by 1 minus sum of yi squared. And actually sum of yi squared is what? So they are here. And so that's how this ugly x0 plus 1 squared will be eliminated. So this is like 4 times sum of don't have much place. Plus 1 squared. X0 plus 1 squared minus dx0 squared. 0 plus 1 squared. I think I lost some minus here, but okay. Probably actually this metric should be okay. Then I just derived Einstein metric, Minkowski metric, but probably but I hope that I will derive the usual Euclidean metric. So here we have sum of xi squared divided by x0 plus 1 squared. And this will give us something. So again, let me extend some for some place here. So here we have, so this is actually what? This is actually So this is actually x0 squared minus 1 divided by x0 plus 1 squared. So 1 minus, yeah. So this is the same thing, and so 4 times of, yeah. What vector square root. Squared, yeah. So here was square actually, yeah. I forgot. So let me, yeah. You should be accurate with computations, which I usually don't. So, okay. So here we have something like this thing, and here we have something like 2x0 plus 2. Wait. No. This is first of all squared. And divided by x0 plus 1 squared. Okay. So this is just equals to sum of dxi squared minus dxi 0 squared. Well, that's actually okay. Mistake. Okay, I made a mistake. So this is how tangents are computed, and let me switch the screen. So actually, this is like an Minkowski metric for Einstein model of relativity, and yeah. So now let's continue for today's topics. So computation so far, we have seen some elementary formulas, some linear algebra and differential geometry. And for motions we had linear formulas, fractional linear linear formulas for Hyperbolic, fractional linear for Klein-Bol, inversions and Euclidean for conformal models, and then those are computed both elementary and with differential geometry. And volume and area, actually we didn't see this before, but this is a formula for computing volumes and also areas in this geometry. So how to do this? Actually, well, when you have a metric tensor, you can compute multidimensional volume as integral over the area, over domain you are calculating, and of square root for determinant of the metric matrix. Okay. So actually, at home I made a computation for the volume of for volume of a ball of radius r in hyperbolic geometry with k equals 1. Actually, here, why there is no k actually? Let me mention it. In this formula for Poincare ball. Actually, when the key here is when you take the ball of radius k. Yeah, or probably 1 over k, or I forgot. But let me think about it. Yeah. So section. So yeah. So ball of radius k. Yeah. Okay. So here you should divide by k squared and heroes. No, here you don't. Okay. So actually, that's an interesting formula for computing a volume of a ball of radius r in hyperbolic geometry, and that's not very trivial, actually, since you don't have your usual Euclidean intuition for volumes of a ball. You just have to somehow integrate this function in this metric. And actually, let's do this since since 2 days ago, even 3 days ago, I had an idea that how to, well, let's have some discussion actually about applications. So how to check that your underlying geometry in your application is actually hyperbolic or somewhat else. Well, actually, you can do this. If you have some data, you can do what? You can sample. Okay, let me switch the screen again and explain. So, okay, so let we have some data, lots of points, yeah, that's usual observations. Those points are lying in some multidimensional space, usually, and so the coordinates are your data, yeah, and how to check that your underlying geometry of your data is somehow hyperbolic. So you can do this. You can draw a ball around some point and consider points inside as sampled points. So how much points there are? So if your ball of radius r, your geometry probably is Euclidean if number of points is proportional to some power of radius. And actually for hyperbolic, so this Euclidean. For hyperbolic geometry, this will be actually much larger. This is proportional to some exponent of r, probably with coefficient, let's say k. Actually, this coefficient equals to dimension, but never mind. And so this is because your volume of the ball of radius r is, so this is hyperbolic. Yeah? In Euclidean geometry, we have a volume proportional to r power n, and in hyperbolic geometry, the volume is proportional to exponent. So it's growing very quickly with radius. So if you are not interested in checking this, let me know. Actually, that's probably some useful notion for data analysis. But okay, if you tell me something, yes, that was some interesting exercise. Okay, so you don't want to check this, no? Yes. Yes, now you are also this kind of person, but tell me something. Actually, I showed you a planar formula, not n-dimensional. Yeah, and I didn't derive it actually. So now actually my proposal is to do this exercise.
That could be interesting.
Actually, so it's not very trivial for n dimensions. I was integrating it several hours before sleep.
Are we supposed to do it in quantum model?
Yes. Yeah. So I wanted to show you some technique actually for doing such things. So actually, you probably seen some scary model. So you see something like, this metric, you should integrate this, and somehow you should derive a formula for n-dimensional volume of ball of radius r. Where should I start, probably? Well, actually, for hyperbolic geometry, there is a standard trick. So, if you are working in Poincare ball, or probably Klein ball, then actually all the points are equivalent to each other. So you just can put your ball in center of your Poincare ball, and then actually radius. So here we have a ball of radius 1, and this radius here is somewhat like a row of r, since we don't have a guarantee that this will be equal to r. Yeah, since why? For example, if you take r large enough, then it will exceed your space inside your Poincare ball. Yeah, so this is some not trivial function. So how to compute it? Actually, the answer is almost written here. We shouldn't. We know that. Let me show you. We know that that length of a segment of any curve is given by this formula, Wish formula. So you should integrate of over from 1 to from 0 to 1 of your metric. depending on t and dt. So this was a formula from third lecture and standard differential geometric formula. So let's do this. So we have a metric like this. So this is like sum of dxi of t squared, and actually there is a mistake. There should be no such thing here, since we already took a square root of some differential of some tensor here, which already containing some differentials. So here we have something like 1 minus xi of t squared. And what's next? So this is the point 0, and here we have rho of r. So let's think that our point is moving with constant velocity, with constant Euclidean velocity. Yeah. So xi of t equals to rho of r multiplied by t multiplied by basis vector ei. So no, but not basis vector, but some constant. So we can also rotate this point and put it somewhere here. So here is the axis x1, and here are all other axes, yeah, and so x1 of t equals to rho of r t multiplied by t, and xi of t equals to 0 for I greater than 1. Yeah? So this is some technique. So let's integrate this. So integral of this thing. So here we have rho of r multiplied by dt divided by 1 minus rho of r multiplied by t, and this is squared. Yeah. And what actually? So we have an equation. So for us, our length equals to r, since we have a ball of radius r, right? Yeah. This is a task. So L equals to r, and this equals to r. And hopefully you all know how to integrate this thing. So this is some difference between what? 1 over 1 minus rho of r t. So here is 1/2. Here is dt minus, here is a bracket, the integral of 1 over 1 plus rho of t. Yeah? Yeah. Yeah? Yeah. Oi, rho of r t. Please correct me if I made mistakes. Okay. So this is some, so those are some algorithms. So this is like, also actually we have rho of r here, since we have it here, right? Yeah, sorry. Okay, so we have like rho of r multiplied by logarithm minus logarithm of rho of r t divided by this constant rho of r. This is, so limits of integration will be put it somewhat later, plus, minus logarithm of 1 plus rho of r t divided by this constant rho of r. And limits are from t equals 0 to t equals 1. So here we have, actually, yeah, I forgot to put 1/2 here. There it was. So here we have like minus logarithm of 1 minus rho of r squared minus logarithm of 1. And so now we have something like this. So we have that this equals to minus logarithm of 1 minus rho of r squared. And we remember this is equals to r, so this is like 1 minus rho of r squared equals to exponent of minus r. So we know that rho of r equals to equals to 1 minus square root of 1 minus exponent of minus r, right? Whoa. Okay. Yeah. Where, what? Division by 2. Okay, yeah. So here we have division by 2. Here also. And so we have like 2r here and 2r here. Yeah. Okay, thank you. Okay. So that's nearly exponential decreasing.
So this frequency being described the meaning of r.
R is a radius of a ball.
Then rho?
Rho is a radius in Euclidean model.
Okay. So r is the distance from the origin in hyperbolic.
R is a distance in hyperbolic geometry. Rho of r is model is a distance in Euclidean model. Okay, actually, yeah. Remember that we have so all the points here are equal on this sphere. So with center of our model, so we have something like this. So this is a pure ball with this center. Okay. So how to do so? Now we should somehow integrate this. Yeah. Okay. So let's compute this determinant first. So our matrix is actually diagonal. It's like 4 divided minus, okay, let me not write the sum here. Let me write it as a norm. 4 divided by 1 minus square of norm. And of diagonal, here are zeros. Okay. So this is 4 power n divided by, oh, I forgot square here. So divided by 1 minus square of norm of x, and all powered by 2n. Okay. So our next task is to integrate this function over a ball, over a Euclidean ball of radius rho of r. Yeah. So let me denote rho of r just by r, by rho, sorry, and let me start computing it. So it's integral of what? Of square root, yeah. So this is 2 power n divided by 1 minus norm of x squared power n, not 2n here, since we're taking square root, and dx1, etc., dx1. Yeah. So omega here is a ball of radius rho, the center at 0. So let's make a change of coordinates. We will make a polar change of coordinates. So xi equals to what? Equals to r multiplied by cosine psi 1 multiplied by cosine psi I minus 1 sine psi I. Right? Those are polar coordinates. So we know Jacobi formula that this integral then equals to integral of what? So integral from 0 to rho, integrals from 0 to So here from 0 to p, from 0 to pi, 0 to pi, yeah, of determinant of Jacobian for this matrix dxi over d psi j's, dxi over d rho, and multiplied by 2 power n divided by 1, not power rho, but 0, multiplied by 1 minus r squared power n. And here we have like dr, d psi 1, etc., d psi n minus 1. So, actually, that's some formula. So, how to do this? Let's compute this after a 5-minute break. So this will be. So for now, you can think about how to do this. The most challengeable part is. The most challengeable part is somewhat ahead. Those were just some definitions. Okay, 5 minutes break.
Вы там, кажется, читали, то есть вы раскрывали вот эту вот,
Да.
как нифига вроде.
Да.
И у вас вот тут минус.
Сейчас. У меня тут было.
Вот смотри.
У меня было вот это.
У тебя было вот это. Если ты к общему знаменателю подходишь, тут рос плюсом, тут рос снова с плюсом. Потом, как
ошибка.
Бы, да.
Окей. Спасибо. We made a mistake here, so I will correct it. There are 3 types of mathematicians. One who can count, and ones who can't. Yeah. Oh. Actually, I was a bit confused when I got this formula, since I remembered the correct one. Okay, let's continue. Actually, I was told that I got a mistake in this formula. Actually, I didn't compute it at home, since I just got the idea of a solution and then yeah, and then I didn't compute it. So okay, so actually there was a plus, so there should be a plus here. So here also should be plus. So here we have something like this expression, and then after solving equations we have this thing which equals to hyperbolic tangent of r. Okay, this formula much better. Okay, so but actually all I have to do is to substitute this formula into what I will get here. So let's move on for computation of our volume. Some interesting integral here. Actually, for polar coordinates, we have Jacobian. So yeah, so this Jacobian is somewhat like r power n minus 1 multiplied by some function of psi i's. And this function is actually is given in the is what we were computing when computing a volume for n-dimensional Euclidean ball. Since you were also computing this volume in polar coordinates, yeah, and so actually what I want to do here is just to get rid of these integrals over psi and say that this is some constant. So this will be a function. Okay, let me show it to you that this will be a function integral over r of what? Of r power n minus 1, some function. Okay, let me actually copy it from Wikipedia. Yeah. So actually, this function equals to, so not on n minus 1, but so this function equals to pi power k divided by k factorial, or there is an expression with gamma functions which I don't remember. K factorial 4p power k divided by 2k plus 1 factorial. Actually, yeah, comes like this. So this is just constant. So this constant is from Euclidean law, since the computation is the same, and multiplied by 2 power n from here, divided by 1 minus r squared power n dr. So actually what we have to do now is just to integrate this function on R. So it equals to integral from 0 to R to rho dr r power n minus 1 minus, so here actually constant depending on the n, here is power n, and yeah. So this constant, well, sometimes it's an interesting, it will be interesting constant, but actually what we usually think of is just asymptotics here. So let's integrate this thing. How it will depend on big R. Yeah. So this equals to what? So here we have, so actually that's some integrals that I was integrating for an hour or two. And here is the idea, actually. Like this, no, oh, maybe I rushed with my conclusions. Okay, no, everything is fine. Yeah, so dr. Okay, how to do this? Actually, so here will be some change of coordinates. Actually, let's check what is differential of this thing. I forgot what I should integrate, but okay. So yeah, so let's compute this. So this is a dr divided by 1 minus r squared plus b dr divided, no, sorry. This is with plus, this is with minus, yeah. 1 plus r squared, yes, and I want this to be, so I want this to be equals to this thing. So let's compute this. So actually this is like b minus b r squared plus 2br minus b. I don't have a place. Okay. Plus ar squared plus 2ar and plus a. So and divided by 1 minus r squared. So in order to integrate this thing, I have to put a equals to b and equals to 1/4. Yeah. So then this differential will be like this. Yeah. Are you following me?
I have one more question.
Yeah.
So what is the square root of the determinant?
Yeah.
Where is it taken?
You are late for the start.
No, I mean
Continuation, but
the determinant itself is correct.
yeah.
Here you have to have the square root of it.
Yeah, sorry. So okay, let's return. Okay, let's return. So we have this determinant, right?
Correct.
Is that incorrect? Why?
Because those are squares of the elements of the vector.
Squares of element. So this is determinant of our metric, right?
This is the diagonal.
Yeah.
No, I get it.
Yeah. So this formula is correct, right?
Yeah, thank you. Now
Okay. And
it's
then we took the square root, and then actually the idea was that I am integrating over a ball, and Jacobian over a ball is the same as in Euclidean. So yeah. So now we have to integrate this thing, and so we have like, again, I should have some place. So we have like d of 1/4 over over 1 minus r, 1/4 over 1 plus r. Yeah. And this equals to actually what? This equals to 1/4 1 minus r squared. Yeah. So what now? Am I correct here or not? Yes, I'm correct here. So now, yeah, so now we have to integrate this thing. Actually, so let me let me first rewrite it. I got somewhat lost, but you can do it yourself. But actually, I hope that you will do this even without me, but probably. Yesterday it seemed correct. Okay. R power n minus 2 something like this. G of here is square. Okay. Actually, sorry, I got lost. Yeah. Yesterday I thought there should be R here. Okay. My bad. What to do now, actually? Then, okay, so let's think about how to integrate this. So here we have like no. Sorry, actually. Is everything alright? Was alright here? Yeah, everything was alright. Okay, okay. Okay, so so probably I made a mistake yesterday when I was computing this, but okay, this is a rational function of power 2n, so it's so the integral here should be, well, actually it is computed, well, actually what? Actually, how to compute this? For now I have no idea because I made a mistake yesterday. It seems so. So we have, yeah. So the idea here is to do this. So r power n divided by 1 minus r square power n. Yeah, something like this, but divided by r. Equals to what? Equals to r power 1 over 1 minus r square power n, yeah? And this equals to what? This equals to 1 over 1 minus r, 1 minus r, minus 1 plus r. 1 divided by 1 plus r. Power n. So this is some rational function. And over of this thing, and the standard theorem is actually like this. Integral will be rational function plus rational function multiplied by logarithms. And so actually I thought yesterday that there should be r here, not just one. Yeah. No, actually, I didn't find it in the internet, so I tried to integrate myself. Well, actually, this is somewhat like computable thing. Yeah, actually, okay. What? Yeah. Analytical integral, but for rational function. Rational functions are actually integrating very well, actually. Very integratable functions. You can read this technique for integrating this in every standard book for calculus. but for general formula, okay. Okay, sorry. I have to record additional video for just doing this, it seems. So let's continue actually then. So that's the main point here will be that actually my main point here was actually to show that this function of power power 2n, rational function of power 2n, so this should be and you should substitute here somewhat like exponents here, so this will be this is an exponentially decreasing function, so the volume here will be like exponential. Yeah, okay, sorry about this. Okay, let me switch the screen and continue, since we have something to talk about. So let's shortly actually we can compute volumes, yeah, and we already computed lengths and angles, motions, and what we might need to work with subsets. Well, the basic question is when 3 points. What to do when 3 points are on the same plane, where several points are on the same subset, or subspace, or some subvariety. Actually, this is useful for differentiation functions, and here also will be some essential hyperbolic analogs for Euclidean functions. Okay. So let's continue for this. So which systems of coordinates we might have? Well, we might have like polar coordinates for hyperbolic geometry. The definition is very standard. And how to compute in this coordinate system. So you might use laws of cosines, which I gave you already. And so implying it for k equals to 1, you get this formula. Yeah. So this like distance between 2 points for in plane. Yeah. Okay. Also, you have Cartesian-like system of coordinates. So if you just take two axes perpendicular to each other, and you take some point in hyperbolic planes, then you draw two perpendiculars, this and this, yeah, and then count the distance from the foot of your perpendicular to the origin of your origin of coordinates. So this is like Cartesian-like coordinate. So yeah, so here is the definition. And in this definition, we have like such formulas, like when you have hyperbolic tangents, sum of hyperbolic tangents of coordinates, sum of squares of hyperbolic tangents of coordinates equals to 1, then your point is ideal. Lesser than 1, then you have hyperbolic point, and if greater than 1, this is not a point at all. and you can recompute between polar and Cartesian like coordinate systems like this is all in plane. Actually, you also might have something like equations for straight lines. You also might have a metric tensor in these coordinates, yeah. So the formulas I like here, like this, and actually this might be useful, but that's not always comfortable since actually what we don't have here. We don't have here like a method for computing in coordinates for like subspace. You have some subspace and how to introduce coordinates here from coordinates on your space. And yeah, actually for the help we will use gyrovectors, but first let me introduce logarithmic and exponential mappings. So, what is logarithmic and exponential mappings? When you the tangent space in a point A, let me remind you definition, is a vector space of all possible vector velocities for trajectories coming through this point. And there is a relation between tangent space to a point and of hyperbolic space and the hyperbolic space itself, since they are topologically equivalent. And this will give us some new coordinates in hyperbolic space with new properties, since vector space is like Euclidean, and hyperbolic space is like hyperbolic. So exponential mapping is what? Is when you have, that's what actually. If you have a velocity v0, you just take some let me just say that this is an integral curve for vector field generated by tangent generated by vector v0, the point, and there's some intuition behind. You might ask me what it is, but actually here is the formula in case you were worrying. So those things that I was saying are again from differential geometry, and so you might take this thing. So this is a mapping from tangent vectors to what? To your hyperboloid. Okay, so let's check that this thing actually is on hyperboloid. Yeah, actually there's some exercise here. So let me.
Can you specify the metric denoted by n?
What? What metric?
Can you specify the metric denoted by n?
Yeah, here it is.
But it is like because 1 minus the
Oi, sorry. Okay. Oi, I was hiding. Sorry. Oi. Yeah, so actually what it should be. Yeah, this should be like this. Yeah, no, sorry. So let me. So if okay, probably there should be more. Okay, I don't remember it. Okay, actually, the best thing to do is to. So I just forgot if there should be minus or plus. So the best thing to do is to compute it in exercise. Okay. So, so I'm translating. Yeah, and I'm streaming. So okay, let's do this. So we know that minus x0 squared plus x1 squared plus etc. plus xn squared equals to minus 1. And yeah, actually, okay. So, uh-huh. Yeah, actually, this formula should be correct. Yeah. So let's check this. So let's check that this thing y is satisfying this equation. Yeah. So how to do this? Let's denote as alpha hyperbolic cosine of square root of Minkowski scalar product of psi, square root of scalar square, and beta denote as hyperbolic sine. Yeah. So what now? So we have like alpha plus beta multiplied by psi over square root of scalar Minkowski square. And what we should do is just to check that Minkowski scalar square of this thing equals to what? Yes, equals to what? What will be sufficient to show here? Equals to what it should be equal to for this point belonging to our hyperboloid. What? Not minus 1. Okay, you can see that the definition of Minkowski scalar product is scalar square is like this, yeah, and we have something like this as a definition of hyperbolic. So what is definition of scalar product of y for belonging to hyperboloid should be equal to to 1. Okay, let us check this. So let's compute this scalar square. So that's alpha square xxm plus beta square of divided by psi m, and here is psi m, and plus what? Plus 2 alpha beta x, so divided by square root of psi m, and multiplied by scalar product of x and psi. Yeah. Okay. So what to do now, actually? So actually, I forgot to copy it, but okay, let me just copy it now. That actually we have that our psi is a tangent vector. So it's a velocity. So actually we already did the computations with it. So let me just say that, okay, wait, that psi I is dxi over dt. So you may think as dxi as psi I multiplied by dt, and this gives you, and let me remind you the formula. Formula is like this. Yeah, do you remember it? Two hours didn't pass yet. So here we have like C0 dt. Oh no, x0 psi 0 dt, and here we have like sum of xi's psi i's dt. So you have like x0 psi 0 minus x1 psi 1 minus x2 psi 2 minus etc. minus xn psi n equals to 0, right? From this equation, yeah? So you have like, and actually this is a Minkowski scalar product for x and psi. and this was here. This thing was here. It equals 0. So we have like what actually? I'm sure that there is some mistake here, but okay. Actually, M should be here, but okay. You didn't notice. So this thing equals to alpha squared x. Yeah. So yeah, everything is right. Scalar square of x. Yeah, there is no mistake, fortunately. Plus beta square multiplied by what? So this is just 1. Yeah, plus beta square multiplied by 1. And let me remind what were alpha and beta. Alpha was hyperbolic cosine of something, and beta was hyperbolic sine of something. So we have the same thing. So this is hyperbolic cosine of scalar square of this minus hyperbolic sine of square root of scalar product psi. And actually this is a fundamental hyperbolic trigonometric identity. Hyperbolic cosine squared minus hyperbolic sine squared are the same things, equals to 1. Yeah? So, yeah, and actually, I am not correct here, since that's not the thing, since again, mistake by mistake. So this equals to -1, so here we have minus, and this equals to 1, so here we have plus. So this equals to -1. So why is what? Why is this minus or why is this plus? Yeah, what? First minus. So this really actually. Yeah, actually, yeah. Sorry. With plus and with minus, yeah. No, with plus. Why? So some mistake probably. Maybe the mistake even in the exercise, but how to yeah. So here then we should have okay. So I wasn't correct. So here we should have this with minus. Okay. So yeah. So yeah, let me improve my presentation now. Okay. Sorry about this. Lots of mistake today. So here is with minus, here is with plus. So now everything should be fine. So we have to check that this thing exponent x psi when substituted to Minkowski metric Minkowski scalar product should equals to -1, and this was like this, yeah? So, okay. Actually, it is lying on the same hyperbolic line also, since actually what? Your points here are belonging to the same two-dimensional subspace, yeah? They are linear combination of x and psi, yeah? So they are belonging to two-dimensional subspace, and this is a section of hyperboloid. So they are belonging to your hyperbolic straight line. Okay. Let's continue. And here is an inverse mapping. So from hyperbolic plane to any tangent vector space, given by this formula. Yeah. Actually, you can check that these formulas are inverse to each other. So the two functions are inverses, are functional inverses of each other. Okay, do you want to check it actually? Or it is like, you know, obvious, or might be an exercise, I don't know. Okay, you don't say anything. I'm not saying anything, so probably. Yeah. So if you substitute this thing into this thing, then you just get y. Yeah. So yeah.
Not that this is too obvious, but this does not sound like interesting to do.
Yeah. Okay. So that's kind of obvious. Okay. Actually, so here you have like two points on the same line, and you just get point on the same line, and here you have something like the other transformation of this type, and probably the inverse to each other. Okay. So now let's move on for final part. Okay. Actually, that was the most complicated topic to study for me. So lots of algebras are ahead, actually. So gyrovectors were invented by Professor Abraham Ungar from North Dakota University. He wrote several very thick books. Actually, the thickest one is about applications to Einstein's special theory of relativity, and several others, maybe not the thickest one, but okay. So actually this is about 800 of pages, and the others are just other hundreds of pages, and they are devoted just for computations and very few of pictures actually. But yeah, so but he's sometimes writing about geometrical meaning of this thing. So okay, let's move on. So context here is just idea for these computations came from both well, actually from three things: from Einstein relativistic theory, from Klein model, which is about lines in a ball. So your subspaces are just linear sections of your ball, and thus they are subspaces. So some linear algebra might be useful, but just not direct approach from linear algebra. And there was some. Actually, I didn't put it in the slides, but there was some function. Some standard hyperbolic motions in plane are just very simply looking, and some of the formulas for the plane will be simply looking. But lots of formulas, and they are huge. And yeah, again about idea. What is gyrovector? Informally, it will be a difference between 2 points in a ball, and this difference is get up to a motion, and so there will be sums between them, and actually those sums are not the sums of in usual meaning. So you don't have such thing as sum of 3 vectors. These 2 expressions will be different, and actually also a plus b and b plus a also will be different. And actually there will be a motional transformation between a plus b and b plus a. So actually, yeah. Okay. So this is a definition of addition of gyrovectors. Remember this is a point of inside the ball of radius c. In Einstein relativistic theory, c equals to speed of light. And also there is a gyrator operator defined by this formula. Actually, in Ungar's books, there are several formulas for sum and gyrator operator, for gyrosum and gyrator operator, and they are different, and he just giving translation formulas between them, but yeah, lots of formulas in his articles and his books. But that's a computational framework actually for hyperbolic neural network.
So can you please elaborate on why the first formula is the same as the second?
Which second?
Second one.
This sort?
Last one.
Yeah, actually, let's do this as an exercise after a break. You can think about it before 5 minutes will be up, yeah?
They are not equal, right?
They are somewhat equal. Actually, they are equal. I just checked it before the lecture, so might be another computational mistake, but okay. Let's have a break and then check. Actually, Telegram, do you hear me? I just realized that I turned off microphone. So Telegram is silent. Telegram, please answer. So, you're all asleep. Ah, yeah. Okay, you hear me. That's great. Do you hear me well, actually? Okay, okay. Since I realized that when I am recording with microphone and with just my voice, then for the recording, the sound is lower. Okay, good. So, okay, dear Meatbags, let's continue. And actually, yeah, I somewhat realized that probably I might have wrong definition for gamma in Mark formula, but okay, let's find it. This was in this article, and okay, so no, actually correct. Yeah, correct formula. But what is V then? Okay, sorry, probably. Uh-huh. Uh, so probably V here is just actually. So I was asked before the break why these two formulas are equivalent to each other, and for now I'm adapting what I said. So they are like equal up to coefficient. So probably let's check this. Now let's switch the screen. Okay. Probably if constancy here, well, actually it should be the same thing, but okay. Let's check everything. So we have like so here we have like probably maybe then they're equal. Okay. So I can't compute in my mind actually. I just realized. So that's a realization just for reading some course. Okay. So what to do here? So here we have like x multiplied by 1 plus 2c xy plus c norm of y square of norm of y and divided by 1 plus 2cxy plus c squared product of squares of norms for x and y and plus y multiplied by 1 minus c square of norm x 1 plus 2cxy x times y plus c squared x squared y squared. Yeah. So actually, what to do now? Let's think about it this way. Actually, this is like some scalar product for what? Probably. Wait, no, this is not a scalar product. Okay. Let's think about it other way. So we have to compute this gamma. So yeah, we should somehow take the square root, and well, okay, probably after taking some recomputing coefficients, probably with what. Actually, I don't know which coefficients to choose, but okay. Okay, so they are somewhat alike formulas. Actually, yeah. Okay, actually, this also might be chosen as gyration, as gyrosum, and let me show you that. There is a definition of gyration. Yeah, definition of gyration in this way. So if you just take gyrator operator is what? Actually, this is a motion for your vector z, gyrovector z, with what? With with this way. Well, this looks like this formula, but probably A, B, and D are different. So you can take such kind of things. So for Einstein relativistic theory, gyrator operator will look like this. Okay. And what about geometric point of view? Actually, there will be some algebra, but okay, let me show you some formula, some geometric meaning. So if you just taking 2 points A1 and A2 and ideal points for line which connects them, then if you take gyrosum, actually gyrosum will be inside the ball somehow, even this one, and okay, so this is a formula from some solving of hyperbolic triangles, actually, inspired by velocity addition formula. So if you're just taking gyrosum with some gyrovector x, then you are just moving the whole line. Yeah. And you are moving it not necessarily parallel to original line. So this looks like this. So this is a Klein model, actually. Ball and lines, yeah. And some explanation is on this link, but okay. So this gyrator operator formula. So there are several laws for gyrator operators and gyrosums. So I said to you that A plus B and B plus A are different. So if you take U plus V, then it is a V plus U with taken as a for gyrator operator of U and V. That's some idea behind the formula why this gyrator operator is appearing. So this is just like a transformation between these two sums. And also actually it is a transformation between u plus v plus w and u plus v plus something. Something is a result of applying gyrator operator to w. And yes, this is again when you are just taking these formulas in these sums, you are just reducing these formulas to something. Actually, probably some physicists just computed this associative law and just derived it and showed it to Professor Unger, and he watched it through. Actually, he was mentioning something about this in his articles. Yeah. So here is also right gyro associative law, and this looks like this, very similar. Also about how to recompute some gyrator operators, like this one, like this one, like, yeah, so what is minus q and minus v here? These are just points opposite to u and v in above, or vectors. You can consider it either way. And gyrator operator of u and v is inverse operator for gyrator operator of v and q. Okay. So actually, let me show you this with some applicable thing.
This is part 3 of my hyperbolic demo, and I want to start by talking about some design philosophy. Remember that 4-dimensional game, the Doctorate? It's been in development for over 10 years now, and I used to think, what could possibly be taking so long? Well, I know now. It's the lack of tools. You want to make a 4D model? Well, you can't use Blender. There's just no 4D editors out there. What kind of file format would you even save it to anyway? There aren't any game engines that would read it. The same is true for render. It has to be all custom. You have to make your own level editor, physics engine, lighting models, optimizations. Basically, everything needs to be redesigned from scratch. And I realized that very early on, the same is true for non-Euclidean geometry. And so all the design decisions I made for Hyperbolic revolved around trying to have ways to use existing tools as much as possible to minimize how many things I have to build from scratch. That plus limiting the scope of the game. That's the only way I'd be able to finish in a reasonable time, and also why I went with Unity as the game engine. There's just more tools and support for it. The first thing I thought about was designing the levels. Building a hyperbolic editor would take a long time, so instead I decided to use a technique called tile mapping. It's actually really common in games, lots of games. Instead of building one gigantic landscape, you just connect a bunch of smaller tiles together to form it. The only difference in the hyperbolic space is there's a different number of tiles around each corner. To make things even simpler, I only use square tiles. And I just changed the number of squares per vertex to get different curvatures at different levels, including spherical. When it comes to placing those tiles, a grid would be really nice because I could just place a tile at, say, 5 on 4, and that's it. But you can't do that with hyperbolic grids. Remember, up right is a different coordinate than right up. Integer pairs won't work. So I just took the lazy way and just represented tile coordinates as a string of steps from the origin. So this would be the RU tile, and this one the UR tile. To build the grid, I start at the origin and then recursively expand in all 4 directions, right first. If there's already a tile there, then I just skip it. In Euclidean space, it's easy to plan out a level of paper, but I can't do that in hyperbolic space because there's no good way to physically draw it out on that paper. And again, I don't want to spend time making a big level editor, so I came up with something easier. Just use the game itself. I just build the entire level with debug tiles that print the coordinates, walk over to the part of the level I'm working on, and then write down which tile goes where and at what orientation. I can preview how that looks, walk over to another section, and then just keep doing it. Less important areas can just get filled in procedurally. It's not the most efficient, but it was fast enough to work. Now I have a big element in the room. How do you actually represent a position? What coordinate system can you even use? And how do you transform the tiles, whether player or objects or anything? Before I answer that though, here's a quick refresher for how this normally works in 3D games. So there's this concept of a transformation matrix. It's a 4x4 matrix that typically represents an object's rotation, translation, and scale. What's really nice about this is you can multiply these matrices together to combine a bunch of transformations into just one matrix that gets sent to the GPU. This makes it really efficient and easy to understand conceptually. Well, it turns out that the same abstract concept of a transformation matrix also works in non-Euclidean geometries, but with something called gyrovectors. If you've never heard of gyrovectors or gyrovector spaces, you're not alone. They're a really novel concept. I couldn't even find a single YouTube video about it. They're so useful. At a high level, it works exactly the same way. It's a structure that has a rotation and translation. It's just that the multiplication part is a little more complicated than the matrix. Luckily, that's all hidden away in the code, so you don't even have to worry about those details. Well, sort of. It has some different properties. Like, normally translations are commutative. It doesn't matter what order you do them. But gyrovector translations are not. Remember, up right is a different coordinate than right up. Also, the resulting gyrovector can end up with a rotation, even though the ones on the left don't have it. That's the gyro part of the gyrovector, and the resultant alignment, which I talked about in the previous video. Gyrovectors are also non-associative, unlike matrices. This is part 3 of my hyperbolic
Sorry. Let me return. I just wanted to say that holonomy is just when you are returning to the same point and something changes, like your direction. Yeah? So you are orthogonal to your previous self.
Previous video. Gyrovectors are also non-associative, unlike matrix transforms, which is kind of weird, but we did drop the parallel postulate, so of course we'll have to drop some symmetries that we take for granted. Anyway, the original paper applied these to points on the Picari ball model, the stereographic version, and so those are the coordinates I used internally. With a few changes, it can also work with hyperbolic coordinates, but for some reason it seemed to lose precision. So here's how the render pipeline looks like. There's basically just an extra step in the vertex shader to apply the gyrovector transformation. This warps the vertices to the correct spots, and ta-da! We're rendering hyperbolic geometry from the player's perspective. And in case you're wondering, to render spherical geometry, it's mostly just changing a bunch of minus signs to plus signs, and hyperbolic trig to regular trig. But there's a lot of really tricky subtle details here. So I'm going to talk about some of those challenges in the next video. Stay tuned for that. Thanks for watching.
Okay. So this is how hyperbolic game coded. Actually, for those of you who are familiar with big group theory, there is a remark that you can construct a Lie group here from gyro sum and gyrators. You can do and also. So actually, actually there is a theorem which I forgot to add here, that gyrator of A and B applied to sum of x and y, or arbitrary AB x and y, is gyrator of AB applied to x, plus generator of AB y to y, so it is like an automorphism. It preserves the sum, sum structure of the sum, and you can construct here this kind of thing from all automorphisms and gyrovectors. This sort of group, actually, this will be a group. And for our case, so this is actually set in this axiomatic system, if you take this as an actions. And
this is part
sorry. Yeah.
So we can define the semi-direct product on G times this group of options. Here G is what? It is basically a space of
space of gyrovectors.
And then, so as I imagine that, when we define a semi-direct product, we want to work with some new space. For example, saying that one group is a semi-direct product of two others. And we have to define some.
So you just need to do what? You just need to define an operation between pairs. So
But what we get after this?
After this you get a group. Actually, this can be checked, and I admitted this, and actually, this is some algebraic checking, and this will be equivalent to group of motions, actually.
Because my main question is that what we get? I mean, what is this product?
Warren's group for our case. Warren's group for our case, this one. This is what we get.
So the space of vectors was hyperbolic space, and the space of its automorphisms is something we don't know before, right? But we have an equation that when it makes this kind of a direct product, we get Warren's group.
Actually, what is gyro sum? Actually, I forgot to add this slide. We already. But sorry, I want to comment some. So what are gyrators and gyrovectors here? So actually, I already showed it to you on third lecture. So this is like, this is like So this is like Warren's boosts and Warren's notations. Your generators will be Warren's rotations, and your gyro summation is Warren's boosting.
So is this matrix B the same as the gyro sum of the vector and the vector E?
Actually, I fear that I think yes. I guess yes. I just didn't check it by myself. It's somewhat alike. This applying the matrix B is somewhat alike taking gyro sum. Okay.
So in terms of Lorentz transformations, how do you imagine this like physical sense of it as addition of the
like
it's not the addition of.
It's like a change of coordinates. You can do rotations and like parallel transport, but those are not very applicable here.
Different transformations of coordinates and for velocity.
Yes. So actually, for velocities,
I mean, what we have here is velocity, right?
yes, everything we have here is velocity
Okay. But we have
and
coordinates.
transformations of velocities. Well, coordinates are just integrals of velocities. I don't know how to answer for you. So the best answer I probably have is this. Okay. Also, you have a multiplication by scalar defined by this formula. And this is what actually? In idea, this is actually, so S here again equals to radius of your ball or speed of light or whatever you want. So here is the formula with hyperbolic tangents. Here you can see somewhat like a conjugation. So you have inverse of this thing multiplied by scalar r and then taking hyperbolic tangent. And here you multiply by some direction. So this is a unit vector, yeah, and this is like choosing a direction for this. S is again it is radius of your ball or speed of light or whatever.
This is a constant from.
Yeah, constant from your model. Yeah. Actually, this can be defined as taking your exponential mapping of R times logarithmic mapping for point x. With zero velocity, with zero initial velocity. Okay. Actually, that doesn't make any sense for me.
Why?
Because if you're taking, maybe probably no.
Because it makes sense.
Yeah, sorry.
Take a point from our space and we go to the tangent space, we scale it, and then we get back to the other.
No, there should be. Okay, I didn't check what it is here.
So it is the origin was from.
Origin. Origin. Yeah, this origin of coordinates. Okay. So this is the center of your ball. Okay. Thank you. Thank you for.
I'm curious. C is what?
Yeah, C is again is your radius of your ball, speed of light. Yeah, so I am switching with some formulas that I copied from different articles.
I have seen an article with this exact formula, but I think C is a constant from metric, exactly like this.
Yeah.
We have C before the first term in it, right?
Mm-hmm.
And that's why we take the square root, right?
Yeah, actually.
I'm trying to clarify exact connection.
Actually, here I probably see probably should be the square of speed of light, probably then. Okay, I don't know for now.
Oh yeah. It would make sense if C is the square of what we call speed of light.
Okay.
For example, the Minkowski method, right?
Yeah, this should be actually this.
Okay.
This should be the C should be the square of speed of light here. Otherwise, it makes no sense. Yeah. Okay. So, yeah. And applied to hyperbolic neural networks, we can define their the Möbius versions of any function. So if we have a mapping between two Euclidean spaces defined on the whole Rn, yeah, we define the Möbius version of F as a mapping between n-dimensional hyperbolic geometries with radius probably square root of c, and here we have something like this. So exponential mapping of f that is taken from logarithmic mapping from x. So this is Euclidean thing, this is like also Euclidean thing, and this exponent takes us to hyperbolic thing. Yeah. So when you are taking the limit for c tending to 0, actually that's again makes no sense. Okay, so actually here we got mistaken. So since this should be 1 over square of speed of light. So okay. I forgot to recheck this before creating this slide. Okay, sorry. So we have something like Möbius versions of linear mappings, and actually, yeah, and they're so you can actually take compositions of them, yeah, since logarithmic and exponential mapping are inverse to each other. So if you are putting inside this function, inside this x as something like another exponent of g of logarithm, you just take exponent of f of g of logarithm, yeah, and this allows us to define activation functions. Actually, for multiplication, here are some multiplication properties. So actually, those linear, those analogs for Möbius analogs for matrices are not fully matrices, since actually we have lots of properties from usual multiplication, like this. Also, gyrator is acting on multiplication as well, somewhat nicely. Your scalar is can take it from outside your gyrator, yeah, and but in general you have no such distributivity property of this multiplication. You can, well, we can check it if you want from definition. Okay, here is some list of properties, and yeah, actually this will give you what? So geometrically, again, if you take expressions like this, so A and B here are just points inside your ball, and T is scalar. So if you are taking expression like this will look like a straight line, inclined model. From T, real. Yeah, T should be real. No, arbitrary real. Any real number.
And what exactly do we multiply by T?
Okay. So here, minus A is just opposite point for A. Yeah. And here you just take gyrosum with some point B.
And then multiply the result by
Then multiply result by t, and then you just left summing is with A. Again, if you just take plus I to the right, plus A to the right, and then this will be different.
But can you repeat this somehow, because this construction sounds strange. I mean, why did we take B minus A in the Gyrovector?
Okay, that's not what I checked here. Actually, usually in Gar's framework, this is essential to taking this kind of expressions for vectors as minus a plus b.
O minus A to be the opposite of A.
Yeah, actually, I didn't check that what will happen if we take b plus minus a. Actually, they are somewhat like, so they are different by gyrator.
This is part
So you see that they are different by applying gyrator actually. And this is kind of rotated version of this vector. But so it's somewhat very similar.
Okay.
This is
What? No, gyrator is it is rotation as it is a function of two vectors actually always. Yeah. So okay. Actually, lots of formulas for solving hyperbolic triangles with gyrovectors. Actually, they are very simple, but let's not overweight you today. And finally, barycentric coordinates. So, in Euclidean case, barycentric coordinates are just what? So, if you take n plus 1 points on n-dimensional subspace, well, you are taking them as linearly independent, independent points. I mean that, for example, vectors from A1 to all other points should be linearly independent. Yeah. And so then we can define barycentric coordinates for any points on this subspace by equation. So we are trying to express vector OT from for like O can be an arbitrary point. You can think of it as origin of coordinates, but it will be just the same, since you cannot any vector QO everywhere, and the equation will be just QP equals to the same thing with Q instead of O, and so this is an equation with M's, and there is a unique solution for this equation actually. So M's are called masses of points A1, etc., and AN plus 1. And then P is a mass center for this set of points. Yeah, so these are like momentums, and you just taking the mass center from this equation. And actually, it's for physicists, I would like to say that it's inverse mass center problem, since you are deriving your masses from position of your mass center. And in programming, it is usually used like taking coordinates in red, blue, red, green, blue model of color. So the more mass, the more blue mass, the more mass blue point have here, the more bluer your point P will be. The more green vectors will have a mass, the more greener your mass center will be, and the more mass on the red vertex here will be, the redder your mass center will be. Yeah. Okay, this is Euclidean case. And what about hyperbolic case? So actually, there is this whole theorem from Ungar, from Professor Ungar. What is invariant mass for Lorentz transformations and invariant impulse. So you just take for points a1, etc., an, and masses m1, etc., n. You compute this coefficient gamma, you find it like this, and substitute and take your mass center. P is given by this expression. And then MKs are just like coordinates for this point P. And actually, why the choice is this? Actually, if you just add x, some gyrovector x to all points, then you can just recompute the whole thing, and it will be the same equation for points x plus a case. This is some nice equation. Actually, the proof is purely computational.
So
yeah,
the trick, like the miracle here, is that in general we don't have distributed CC, but if we compute left-hand side and the right-hand side, they coincide.
Yeah, actually, they coincide, and actually, let me note that here is just Euclidean sum, not gyro sum. Yes, this is Euclidean sum, and here is, so if you are taking co-invariance of this mass center definition, then you just take gyro addition.
Okay, but
here.
Since it is Euclidean sum, it is important to model hyperbolic space with So is it supposed to be
Klein model.
Klein?
Yeah, Klein model. Actually, you can check that mass centers should belong to a plane which is generated by points a1, etc., an.
But this direct summation.
No, this is this.
No, I mean this is regular summation.
This is regular summation.
Summation.
Yeah, actually, this. Yeah, so this is some identity. when substituting some gyrosums.
I'm trying to clarify the concept of gyrosummation because it's not connected to any of models of that, right? Because a sequence of Euclidean operations.
No, it's somewhat like preserving plane model.
So it's mainly about plane.
Yeah, it's mainly about plane model.
Because before we did not have.
Yeah, before.
The plane model was not that convenient for us before.
Yeah. Actually, the visual thing about conformal models is very clear. Yeah, you can. They are very intuitive, but somewhat curved. And plane model is just like more convenient for computation since it's first planar or like subset in some Euclidean space and or ordinary one, yeah, and and here you just take some affine subspaces. So this.
So if I write masses, would it form a regular affine subspace?
Yeah, actually, you can check it even now. So you might try to prove this since this is the last slide in our course.
That's quite clear, yeah. Because the operations are Euclidean.
Yeah.
Everything that involves mass is Euclidean.
Yes.
Okay.
Actually, yeah. So why this P belongs to this subspace? So actually, the sum of coefficients of a case just equals to 1. Yeah. So you have mk gamma ak multiplied by divided by sum of mk gamma ak's. Yeah. So the sum of coefficients is just 1, and the previous slide you probably noted that the sum of coefficients here is also 1. So
we have discussed it for too much
okay.
time.
So actually, what usage of barycentric coordinates? Actually, about the usage of it, it is like, well, first of all, there are you can define different barycentric coordinates for hyperbolic geometry. There is an article which I didn't manage to read about this. You can find it in the internet. And yeah.
4 minutes.
What? 4 minutes, yeah. Yeah. This is a white slide. Okay. So this and about these barycentric coordinates, even any barycentric type, even any method for defining barycentric coordinates will give you somewhat like hyperbolic analog of k-means algorithm or something like other. So you just may work with your linear algebraic algorithms in hyperbolic space with it, or at least you can define some analogs. And so this was the last thing I have to say. Okay, thank you for visiting the course. Actually, probably you have some questions you want to ask. Actually, that's somewhat like very somber course that appeared to be, and I will upload homework probably today. It will be just very simple, I hope.
Many things that I was curious about is the motions of the n-dimensional hyperbolic space.
So,
And recently we have received
motions of n-dimensional hyperbolic space. Yeah. So what?
recently we have received these formulas. So is this for you have explained that we can just project we have from the hyperbolic space to the tangent to the origin. Then
This won't be a motion, actually.
yes, that would be a combination of rotations and direction.
Sorry, if you take exponential mapping, you just not going to have any motion. So no exponential mapping. Exponential mapping to the start of origin.
I have not formulated the question.
No, that's not rotation at all. Okay.
So if I wanted to describe all the morphisms of the hyperbolic space,
Yeah.
what do I do?
No, if you want to describe all the motions of hyperbolic space, you can do like this thing, or several theorems about it. So this Lorentz group preserving this quadratic form, or it is generated by these things, or it is generated by mirror symmetries, or it is generated by movements of n+1 points.
Basically, yes, if we go logical and fine, but then we discuss the theory of Gyrovectors.
Yeah.
So, how can I make it?
To what?
To the group of motions.
Actually, gyration operators are motions of this way. Yeah, gyration is a motion.
Here, it means in one is
Miraculously, yeah.
so here, the prior of x and y cannot be expressed as a sum of z and something, right?
Well, this is z minus something. Z is depending on
This something is a pretty complex function of x, y, and z.
well, very complicated function of x, y, and z.
And this leaves limit is scalar, right?
No, here you can see x, here you can see y.
It has a scalar part. Which is the first term.
Yeah, scale apart. Here.
And
This is a vector
efficiency
thing.
are Euclidean, right?
Additions, yeah, Euclidean. Everything here is Euclidean. But points will be, all points that are mentioned here are hyperbolic
And just to simplify
in
it
above.
for the complete picture in my head, I mean, these x, y, and z. For two-dimensional hyperbolic space, are these, do they have three coordinates or two coordinates?
Which coordinates do you mean?
For example, if I want to clarify this, what are the coordinates of x, y, and z? I can imagine
Whatever you take. Whatever you take, actually. So, actually,
I mean, I can take one-to-one models,
yeah.
model, or I can take
Ah, so,
what are the coordinates?
so actually, yeah. Since I just decided to copy these formulas from article devoted to hyperbolic neural network, not from Ungar's articles. So this is probably, well, this is hopefully for a Klein model, and but actually Ungar's formulas are about Klein model, definitely. And for these ones, we have to check it somehow. It's not that complicated to check, but that's some work. So actually, Professor Ungar worked on it for nearly 40 years. So this is some.
You mean this is complicated?
Well, no, this might be some genius formulas, but actually, some physicists even before him derived something like this.
And it appears to be very useful for computation.
Yeah, actually appeared to be helpful.
Okay, and the last question I have is that,
Actually, yeah, this last thing I want to mention that hyperbolic neural networks are usually, well, sometimes faster than, really faster than in their learning rate speed as than usual ones. So actually, yeah, use them, but there are still field of study since for some uh, for some well, in some cases they are still not so fast, and this might depend on something we don't know yet on what, but
okay, but just to use it, personally, I don't study hyperbolic neural networks, that's why I'm asking.
yeah.
But here, X, Y, and Z are points from Lang model.
Yeah, points in the ball. Yep, X, Y, and Z are points in the ball. Actually, yeah. If you want to study it more thoroughly and want to have research in hyperbolic neural networks and in some in mathematics behind it, you probably should read Professor Ungar articles or books and just solve exercises from there,
And then I will understand it.
and then probably you will understand more.
Okay. Yes, thank you.
Yeah, actually, um, this is this is somewhat complicated topic, but I just gave you some introduction. Actually, this was actually I searched a lot for some interpretations of what is happening here. So, uh, yeah, if you are just reading random on Professor Ungar's article or random Professor Ungar's book, you just you probably will be just lost with most of these formulas. You need some motivation. Okay. Any more questions? Okay. So if you have any other questions, please write them in chat or ask me personally. Thank you for listening to the course, and good luck with your homework. Thank you.
Well, thank